Hello everyone, welcome back to another OpenFOAM video in Codynamics. So in this video, we will be looking at a solver called rhoCentralFoam. So what is rhoCentralFoam? rhoCentralFoam is a compressible solver. This is also transient. The compressibility is based on density. It can handle heat transfer as well as turbulence, and it is also good at shock capturing. So what type of solver is this? It's a compressible solver which can be used in situations where there will be shock appearing, like aerospace kind of applications. If you are designing nozzles, shock tubes, so in those scenario, rhoCentralFoam could be very handy. So in this tutorial, we will be seeing how to set up a basic rhoCentralFoam simulation, and we will be looking at the post processing. Okay. So for that, I will go to the tutorials. Under tutorials, we have compressible. Under compressible, we have the rhoCentralFoam. By the way, I am using version 2406. You can use any ESA version and follow this, but if it is foundation version, it could be slightly different. I prefer using ESI, so I'll proceed with it. So under rhoCentralFoam, there are many tutorials, but I'll be choosing forward step because it is pretty straightforward as the name says. So I'll copy this and I have pasted the same in a new folder. So the same forward step. Okay. Now before we do anything at all, I will launch my terminal in this location. You can do this in Windows 11 and I will type WSL. So I will have the Linux terminal for this location directly without navigating. So it's pretty handy for me. So I always do this. Okay, once the WSL is loaded, we can start looking at the case. First thing which we have to ensure is that go inside the control deck and ensure that it is rhoCentralFoam. I mean, we copied from there, but just to see that it is rhoCentralFoam, we visualized. Yeah, so it is fine. Now we can proceed with the mesh. So before understanding what is happening in the forward step, we can have a basic idea. We have seen backward facing step while doing normal simulation while learning CFD. But forward step is something quite the opposite. Here there will be a flow and suddenly there will be an obstacle. So there will be sudden contraction. So because of sudden contraction, there will be pressure differences and that will form shock waves. That is what we are trying to do here. So we will open the block mesh deck. In this case, the mesh is generated using the block mesh deck. As you can see, it has three blocks and it has inlet, outlet, bottom, top, obstacle. So these are the patch names, and we don't go in depth on these vertices as of now because this tutorial is not of block mesh deck. I'll just generate the mesh directly and we can see what is the mesh directly. So I'll go here and ensure that we are in the current directory. We have to see 0 constant and system. When you type ls, then I will generate the mesh using block mesh command. Okay, now that the mesh is generated, we can start visualizing it. So I will do the command touch space para.foam, and that will create me this para.foam file, which is a ParaView file, and I can double click and open it in ParaView. So in recent updates of ParaView, whenever you open it, it gives two para.foam. So I usually delete one, select this, click on apply, because when we have two geometries, sometimes the overlapping causes some issues. Okay, so as we expected, this is the geometry. It's quite opposite to backward facing step. At the mesh. So this is a okay mesh. Not very fine, not very coarse. This is some good mesh to run the simulation and it's a 2D. Okay, now let's see what is the inlet, outlet and all. So before that, let's see what is the group empty. So the front and back is the empty group. And then we also have a symmetry plane group, which is this and this, top and bottom. Okay. Now we can see what is the bottom face. As you can expect, this is the bottom and this is the inlet, and the obstacle is this L-shaped one. So this will act as the obstacle which will cause the sudden contraction. We have the outlet, which is this, and we have top. Okay. So unlike what we generally do, Here, this front and back faces are not named as front and back. They have kept it as default faces because it allows you to not choose anything in the block mesh dict. They did not give any default faces. So whatever is not named will go directly into default faces. And that is pretty handy. You don't have to define front and back painstakingly because there are three blocks, which means you have to do three faces for front and three faces for back. All that is painstaking work. So they just left it as default. If you want to change the name, we can change that in boundary file. But we are not going to do that. We are just trying to keep it very simple. So we will proceed with the name default face. Now we got hold of the understanding of the geometry. So I'll close this. I'll close block mesh also. Now let's start looking at the actual case. Let's go to the boundary condition files. First, let's see the velocity. Okay, here you can see that the inlet has 3 meters per second velocity inlet, and the outlet type is inlet outlet, and the value is also same as the inlet. And the internal field initialization is also 3 meters per second in x direction. So it's pretty straightforward. Top and bottom is kept as symmetry plane, which means it's not a wall. Whatever comes in just goes out. And that is what we would expect in a shock tube to happen when we do these kind of simulations. So it's okay. And the obstacle is kept as slip. It's not kept as no slip. It's kept as slip because this is like a compressible simulation. And the default faces are kept as empty. So just like what we do for front and back. That is for the velocity. Now looking at the pressure, we have pressure inlet because this is compressible flow. Have pressure inlet as well as velocity inlet at the inlet, and outlet is kept as zero gradient, which means it will be calculated by the solver. The bottom is symmetry plane, top is symmetry plane. That is also like whatever we did in velocity, it has to be carried over to the pressure also in terms of symmetry and empty planes. And the obstacle is kept as zero gradient because we already defined a velocity as slip, so it has to be zero gradient in pressure. Since this solver also handles heat transfer, we have the temperature file here. So in terms of temperature, we can see it's 1, right? Looking at it, like this is meters per second. Yeah, like we can understand that velocity is meters per second, and pressure is kg per meter second square, which is like Newton per meter square. It's the same as pascals. Okay, understandable. But what is this? It's in Kelvin, but we are talking about 1 Kelvin. How is this even realistic, right? No, it's normalized. So what we are doing is we are keeping the temperature range as 0 to 1, and then we'll normalize the properties of the fluid, such as the specific heat and dynamic viscosity. So when we alter these things with correspondence to the temperature, we can keep the temperature range between 0 to 1, and we can change those properties. We will look at that. And this is called as normalization. This you could have covered in any basic thermodynamics course. So looking at the temperature boundary condition, inlet has like maximum temperature inlet. Outlet is also getting maximum temperature outlet. So it's inlet outlet condition. So that is what we would expect. Obstacle is zero gradient, which means we are not giving any temperature initially. So it's all kept at maximum temperature at the beginning, and the solver will calculate the temperature at the obstacle based on the pressure. And top and bottom is symmetry plane, default faces is empty, just as usual. Okay, that is it about the boundary condition. Now talking about normalization, we can go into the folder called constant. Here we will have two files. First, let's see thermophysical properties. In thermophysical properties, we will have a lot of parameters, but we have this small comment given by the forward step. You can see that these are the properties for a normalized inviscid gas for which the speed of sound is 1 meters per second at a temperature of 1 Kelvin and gamma is equal to 7 by 5. So this is the assumption they are taking in order to normalize these properties. So we will look at everything here first and then we'll come for these. Okay, so to understand what is this thermotype, you can look at this documentation. Okay, by the way, this is the symmetry plane documentation if you want to look at water symmetry plane. And this is the thermophysical properties documentation. Here you go, and we can see that these thermophysical properties are constants or functions of temperature, pressure, and composition. Okay, basically it is the definition of properties of the fluid which we are using. Okay, now let's go one by one. First is equation of state. The equation of state has two types. This is perfect gas as well as icopolynomial. You can read the description here. I will just cover with the name. So the perfect gas is what we will be using here, because ours is a perfect gas, that is the assumption we are taking. And next comes the thermophysical properties. So in our case, we are taking constant thermo. So there are many types: H constant, E constant, and all. So we are taking H constant because we are assuming that it's a constant specific heat model with evaluation of enthalpy. The other is E constant, where the evaluation of internal energy will come. There are also other polynomial thermotype which will change the polynomials as a function. So we are not going with those. We are just keeping it simple. So we are taking it H constant. Now, then comes the thermophysical properties for the species. So in our case, we are just keeping it as a single species. So no change in that. And then comes the transport. So here there are a lot of transport properties like constant, polynomial, and Sutherland. Here we will be using constant. So the constant is like we will have transport properties set constant. It will not change with respect to time or any other parameter. Then coming to the mixture, here we are dealing with a single fluid. There is no mixture, so we will take a pure mixture. But if we are dealing with any sort of chemical reactions or combustion modeling, then you might be interested in other types, which will be covered in other solvers. And then coming to the thermo model, here we are using HE psi thermo. So HE psi thermo is general thermophysical model calculation based on enthalpy or internal energy and compressibility. So that is what we are using here. And there is a short example on how to use this. That is what this structure also follows. And there are more documentations and explanations which you can just look over. And now coming to this, after we normalize, we are getting the molar weight as this, and the thermodynamics, a specific heat as 2.5, and this is the heat of fusion. There is no chemical reaction, so we can keep it as 0. And the dynamic viscosity is taken as 0 because it is taken as inviscid gas. Okay, and the Prandtl number is taken as 1. So these are the assumptions which was taken while making this tutorial. So if you are working with other assumptions, you might probably be interested in changing the temperature to actual scale, like in Kelvin scale, 300 Kelvin, 500 Kelvin, whatever it is. And in that case, you will be putting the actual values for these properties as well. Okay, that's it for the thermophysical properties. Now coming to turbulence, this tutorial just handles laminar to keep it simple, but we have seen how to make a turbulent setup already in other tutorials. So you can follow those tutorials and change this to RAS model or LES model, and you try to change it to turbulent case setup. Okay. Now going to system. Again, let's look at the control deck. So here the start time is 0, okay, and the end time is 4 seconds. The delta t initially is taken as 0.002, and then the write interval is taken as 0.1. This is okay. And then the purge write. Purge write is like you will delete all the files except for the recent 10 files. So in by default, this is like 10 for this tutorial, but I'm going to keep it as 0 because I want to see from the start till the end. I'll keep it as 0. And the write format ASCII, everything can be kept as default. Coming to adjust time step, they are doing adaptive time step. So this is set to yes. So adaptive time step takes two more parameters. One is maximum CO, which is the maximum Courant number. Here it is taken as 0.2, and the maximum delta T, which is safe to keep it as 0, which is safe to keep it as 1. Okay, nothing more than 1 delta T is like meaningful. So 1 is the maximum delta T. Okay, so that's it about control dict as well. Make sure to save the file. And looking at the FB schemes, you can just look at all of these documentation if you want to understand why they use these. And coming to FV solutions. We are using diagonal solver for the rho U, and rho E. And coming to U, we will be using smooth solver Gauss-Seidel method. And number of sweeps is kept to 2 and tolerance is 1 U minus 9. Relative tolerance is 0.01. Coming to enthalpy, it is using the same solvers as velocity, but the tolerance and relative tolerance are more constructed. Okay, so I'll now go to the case setup actually. Okay, now to run this, all you have to do is rhoCentralFoam. You can run it. It will start running, no issues. But it's going to take a bit of time, right? So let's also cover how to do the parallel computing for this. So I am taking a decomposed particle file from this location, simple foam airfoil 2D system. I'll copy this, put it in the system of our forward step, and I will use the decomposed particle. By default, it comes with this. Now my laptop has 8 cores, 8 physical cores. So to check that, you can open your task manager, click on CPU, and you can see here it says cores. So I have 8 cores. I'll be using 8, but I'm not going to use hierarchical. I'm going to use something called Scotch. So this will automatically try to keep the number of cells for each processor same. So if you don't know how to do decomposing and run parallel computing, I have made a video on that. I'll give the link in the description and you can check it out. I will save this file. If you don't know how to do parallel computing, just follow this for now and you can see that video and understand it better. Now I have to do decompose par. That will decompose the entire domain into 8 processes, which will happen in parallel. And to run the solver, I will do mpi run np8 rho central foam parallel and then press enter. Now this will run. So let it run, and once it is over, I'll get back to you. Okay, the simulation is over now. So now let's take a look at how to post process this. Now, if you come to the location, you will have the multiple processor folders. If you run parallel computing, of course, and you will have all the time steps here. But this is in 8 different processes. So to combine them all, the command is reconstruct par, press enter, and that will start reconstructing the files, and it will output the time steps. Like the first time step is 0.1. You can see it reconstructs and it gives 0.1. And similarly, it will do for the next time step. Let's wait till it is doing. As you can see, it is doing like this, but it will do that like this for 0.1 till 4. Okay, so that's going to take a pretty lot of time. So I'll stop it right here and I'll tell you another method which you could use to post process without reconstructing. So just open the para.foam file, the ParaView file, and just delete one, apply. So you'll see something like this. Now you go here and change the reconstructed case to decomposed case. Click on apply. Okay. Now you insert a slice, probably in Z normal, hide the plane, click on apply, click on Z. Now if you start display, you can see, right? So I hope this helps. We go to temperature, and then we have our velocity. The colors might look slightly different for you. I have chosen a different color now. Okay, and then we have our density. Sorry. Okay, so we have visualized everything. I hope This helps. I hope the tutorial was helpful as such. And if you have any comments, please drop down in the comment section and check out the parallel computing video if you haven't already. So if you enjoyed the video, kindly drop a like and consider subscribing to the channel for more such videos. See you in another video. Thank you.